All right, continuing along here. This example here is just quickly showing you some of the notation and what the area looks like. So for all of these, all three of them, you can draw yourself a normal curve or an approximation of a normal curve. And what I want to do is I want to color in the area for the following distributions. So if this is my mean, the first one's 1 standard deviation. So this would be, up here would be plus a standard deviation minus a standard deviation. So this would be the area we want to calculate. Now, when you do the z-score table that I just previously talked about, it talks about the area from wherever we're talking about all the way down to the origin. So when we do our notation here, we're going to start moving toward our probability of this value right here to this value right here. So we always go from the lower end, so from the mean minus sigma notation, and our x value's got to be between that and plus one standard deviation. So the x minus sigma is our value right here, and the x bar plus sigma is right here. So that notation tells us that the area is a range between one point and another. Similarly, if we go to 2 standard deviations, so we move it out even further, so I'm just going to call that 2 and that 2. That means that we're looking for the area between those two boundaries. And again, we need to transfer it or tell people that we want to go from the mean minus 2 standard deviations, and our data has to be also less than the mean plus 2 standard deviations. So that's that range. So we start using the notation you learned in grade 11 with domain and range. Very, very important in this. And finally, the 3 standard deviations looks very, very similar. I just want to remind you that the area in question here is not the entire area under the curve, but it starts at one location, so it starts at the bottom end. So it starts at the mean minus 3 standard deviations and goes up to 3 standard deviations. And again, I'm going to show you how that transfers over. Now with the normal distribution, the notation, we talk about our independent variable is normally distributed around the mean and the standard deviation squared. So whether it's s squared or sigma squared. Okay, and just quickly talking about the notation here. So there's your standard deviation. So it's going to be a numeric value. There's your mean. The n tells us it's a normal distribution. And this terminology here tells us the independent variable. So whatever we're looking at. So the independent variable is normally distributed with a mean and a standard deviation. So it tells you all that information in that notation. So you do want to make sure that you have this notation on your cheat sheet just to remind you what information is being presented or provided to you. So our first example, and I've got a typo here. I want to calculate, not standard deviation, I want to calculate the z-scores. Okay, so if you can change that to z-scores. So we want to calculate the z-scores for the following if our data x is normally distributed with a mean of 72. Now be careful, that 81 is not written in the right form. If you look back on the previous slide there, it needs to be in this form. So we need to rewrite it. So our data is normally distributed with a mean of 72, so that's fine. But I got to write it as being squared. So what squared gives you 81? Well, it's 9. So our S value is 9. So now we can go ahead and answer the question. So I want to know a Z-score, x equal to 68. So Z-score formula is the data point minus the mean divided by your standard deviation. So for A part, we would have 68 minus 72 divided by 9. So this is going to give us the Z-score, the number that we would go to find in the chart. So 68 minus the 72 divided by 9 gives me negative 0.44. I just want to sketch that very, very quickly for you, just to remind you where that falls. So that Z-score, if I draw a normal distribution, and I say here is my mean, negative 0.44, that value is going to be over here. So what we would be finding is this area right here for negative 0.44. That's what that Z-score would give us. Okay. With B part then, same process, x minus x bar over our standard deviation. So now our data point is 92. Take away 72. We divide that by 9. So 20 divided by 9, and that's 2.22. So it's positive this time. So again, just to give you a sketch, if we went and read the Z-score chart, here's our mean. 2.2 is going to be way up here, so we're going to be finding this area all the way back to the origin. Okay, so those Z-scores allow us to find a probability or an area according to those particular X values. All right, so we're going to be putting this together in a second. So one last example. For each of the following, create a sketch and determine the percent of the data that lies within the following. So A part is 1.5 standard deviations. 1.5 standard deviations. So with the 1.5 standard deviation, sorry about that. So A part for 1.5 standard deviations. So for A, 1.5 standard deviations, we know that 68%, so one standard deviation, we have 68% of the information, the probability, whatever we're dealing with here. It's generic at this point. So if I take 100% and I take away that 68%, it leaves me with 32% left over. And because it's 1.5, I know one standard deviation gives me 68. This is what's left. So 0.5 of a standard deviation is equal to 16%. So therefore, 1.5 standard deviations is equal to the 68 plus 16. 68 plus 16, 4, so 84%. Okay, so the question again, all we're looking for is the percent that lies within. Okay, and we want a diagram with that. So with that particular example, if this is our mean, 1.5 standard deviations, so if this is a standard deviation and this is a standard deviation, we want 1.5, so that means we're not quite getting to the 2 mark, so we're going from here to here, so the halfway point between 1 and 2. So the area, the 84%, or 0.84 or 84% probability, that is the area right there that we would be dealing with. Okay. So on to B part. So with B part, we move to Z scores now. So with the Z score, so B part, Z score equals 2.1. So with the Z score 2.1, if we start with a diagram, which I always feel more comfortable with, it means that here's our mean, and Z score is positive, so that means it's going to be a score over here somewhere, 2.1, and we want to find the percent of the data that lies within that score, that Z score of 2.1. So we are looking for this area right here. So that means we need to go to our z-score chart, and we're looking at 2.1, so you pull that piece of paper out. So z equals 2.1, so I got to scroll down here until I find 2.1, and I kind of need the top as well. Oops. Where's my heading? Can I get it both on there? Not quite. Almost. So anyway, so z equals 2.1. It's really 2.10. So here's 2.1. 2.0 is this column right here. So scrolling down, we got 0.9821. So going back to our note here, therefore, 98.21% of the area is, oops, for a z-score of 2.1. All right. So all we're doing is we're taking that z-score and we're going to the chart. All right. So I'm not going to bother dealing with C and D at this point in time because I want to move on to the final phase here. And I'm going to have to do that final phase in one last segment or last example. So I guess just summing it up here, what we're going to do is on the previous slide here, I showed you how to calculate your z-scores. So now this is how your z-score is calculated. Okay, you know how to calculate the mean. You know how to calculate standard deviation. So all that's known information now. So we're tying it together. So you're using it to find a z-score. That z-score then is being used to look up a chart, a value in the chart. Okay, and that value that comes from the chart is right here. The area from that chart is the same as the probability. So everything's starting to link together for us. So it's important that if you know you have a normal distribution, you need to know the mean and you need to know the standard deviation, because we can use a chart then to find the corresponding probabilities. So I will finish with the last example here in the last segment.